All right, guys. Hello and welcome to the Tech Report podcast. Jordan Drake, our usual host, is not with us tonight. He is out sick, and I think suffering without us, and suffering from some mysterious illness too. So, anyway, we're gonna have to just press on without him. But with me here is Jeff Gazier. Say hello.
Hi.
And Jeff Campman. Hi. So we have two Jeffs, and from here on out, we're going to be completely confused, but we're going to do what we can. So I'm Scott Wasson. This is the Tech Report podcast. Tech Report is, as Jordan would say, the number one place for news and reviews in the computer hardware world. And we have a full slate of things to talk about tonight. So let's get right into it, guys, with a listener mail question. And this is maybe a stumper just because I don't spend a lot of time on this. But let's see. This is Jordan has passed this along to me. It's from a JSON-X12. He says, "Hi Jordan, my forum name is JSON-X12. I'm in the market for a new laptop and I'm having trouble deciding what to get. I've been trying to research the GTX 900 Series M laptops for the last 2 months, but performance benchmarks and comparisons are hard to come by. I would like to at least be able to play GTA 5 at low to medium settings at 1080p. My current one can't even handle AAA games that were released in 2010 at the lowest resolutions. My budget is around $1,000, and I wanted to know if a laptop with a 960M would be the best option for me to go with. I have my eye on the MSI GE60 Apache, which has a GTX 960M with 2GB of GDDR5 and a Core i7-4720HQ for $999. Thanks for any advice." So guys, what would you tell them?
Not having played Grand Theft Auto or used the GTX 960M, I'm not entirely sure. I can say that the 960M is it appears to be based on GM107, which is the same Maxwell chip in the desktop version of the GeForce GTX 750 Ti.
Is it? It's not based on the 20. Oh, really? Okay. That's not a bad. That's a bad. That GPU is not bad for 1080p.
Yep.
Yeah, that's what
I just don't know how it does in that thermal envelope for a notebook. It's a little different than a graphics card, but
yeah, Mr. Campman, you were going to say?
Yeah, I mean when we wrote up the 960M originally, we talked about that, and it's similar silicon, but I think I think it would at least play maybe at 1080p Grand Theft Auto 5 because G5 system requirements, I don't think they're like that extreme.
No,
but again, it's a mobile system. So
I had to think that particular setup for $1,000 when your budget is basically $1,000 sounds pretty good. But I haven't spent a lot of time looking at. I haven't looked at the specs of this GE60 laptop. I know MSI has made some good gaming laptops lately, and that seems like a good GPU to get. And that's a fine CPU. I think it's fine. Core i7 is going to be good. So I think it's not a bad choice, but I should probably have read the specs on this laptop before we started, and unfortunately I did not. So I don't know. My thing is just I look at that and I'm like, let's rubber stamp that because I think it's okay. If you're kind of looking for permission to go on, that particular GPU is not a bad choice for gaming, and it makes sense for low medium power envelope laptops, and it probably will run at medium quality settings GTA 5 based on everything I've heard about how intensive that game actually is on the PC, which is apparently it's nice looking, but I don't think it's the hardest thing to run at decent settings. So let's move on because we were not very helpful to that guy, and maybe get into something that I think was the top request, guys, in the comments for us to discuss tonight, which is the leaked AMD roadmap information. And Jeff, one of you Jeffs, wrote this up. So take us through, what is this that we're seeing here?
Well, this is supposedly a set of slides from a financial analyst day that's supposed to happen on May 6th. It sort of lays out AMD's plans for 2015 and 2016 on both the desktop and mobile side of things. And a lot of the stuff on the 2015 slides, we've sort of seen these before. In some cases, the CPUs aren't out yet. Like there's one called Godavari, which is a successor to Kaveri, which is basically just looks like a speed bump, an extra couple hundred megahertz for most of the chips. And then there's the Carrizo APUs that are coming to mobile, again, stuff that we've heard of before. But the big stuff happens in 2016, where they've got a whole bunch of 14 nanometer processors, including a successor to the FX processor. So this will be not an APU, a straight up CPU. It'll apparently feature up to 8 Zen cores. That's AMD's new x86 core. And it's going to be a socketed chip with a new FM3 socket, according to these slides. We don't know much about it other than the code name, Summit Ridge. But that is supposed to come out in 2016. I think that's kind of been the FX successor that everybody's been waiting for.
Yeah, so Zen is the exciting thing because it's a new x86 architecture for CPUs that replaces Bulldozer, that hopefully gives us more performance. And there's been some other leak slides too, I think.
There were some block diagrams that leaked out about Zen that were sort of not terribly detailed, but I think are from the same deck as these roadmap slides.
Yeah, I think they show like four cores grouped together with a shared cache and some stuff like that. But it is kind of exciting to see. There's some interesting things about this. If this is maybe somebody made this slide up. It may not be an official AMD slide. We have no confirmation of any of this stuff. But assuming that maybe it is, the interesting thing is that Zen looks like it goes from, this is a new core, and it goes from the low power small form factor envelopes that are currently served by the Puma stuff and all of that, up to the sort of mid-range stuff where you have FM2 now, to the high end where you have the FX processors now. So this is a core that spans a lot of space, and presumably, Jeff, that means a lot of power envelopes too, right?
Yeah, they don't actually list the power envelopes for the desktop chips, but they do on the mobile side, and they've got a couple of APUs. One is called Bristol Ridge, and another one is called Basilisk, if I'm saying that right.
Basilisk.
So Bristol Ridge is
like any fantasy novels or anything. Like, come on.
No. That's my problem, apparently. So the Bristol Ridge is 15 to 35 watt, and the other chip is 5 to 15 watt. The interesting thing about that is, whatever you want to call it, is replacing Carrizo L, which is a Puma-based quad-core chip that only went down to 10 watts. So it looks like in this kind of low-power envelope, they've got a chip that scales further down than their previous entry in that space. So it does look like a flexible core, and these APUs. There's going to be desktop versions and mobile versions. The desktop versions will have the same FM3 socket, according to the slide, as Summit Ridge, but they'll have next-gen GCN graphics on board. So it'll be an updated GPU and an updated CPU component.
Yeah. Now, see what the exciting thing about that is seeing the Zen core go into the small power envelopes, because to compete with Intel, they need to be able to get into the small power envelopes with their bigger core, and presumably Zen is going to. We don't know yet about performance, but presumably you'd want it to perform like a Haswell or a Skylake. Heck, just matching the current Haswell stuff would be a huge improvement for AMD, and then get into those power envelopes like the Core M does, so that they can get into ultra-thin laptops and maybe tablets and all those places where you want to play. And to go from like kind of the current situations where they have this split of two architectures, and the low power one is really slow, and the bigger core is faster, but it's not that fast, and it uses a lot of power. To go from that to this situation potentially where your big core can squeeze into really small power envelopes probably means good things for your CPU architecture. And just sort of your ability to take, if you can fit into low power envelopes, then you can probably create products that are compelling and take them up a little bit. We'll have to see how far it can scale and all that stuff, but it's a good sign. So, and what is it? There's some SoC versus not SoC tags on here. What's that?
Yeah, it's everything basically but Summit Ridge, which is the FX replacement, has this little SoC icon. And it's interesting because Kaveri doesn't, or Godavari, which is the Kaveri replacement, doesn't. So it does imply a greater level of integration, if not sort of at the CPU die level, than maybe at the package level than we have with existing processors now. Which is interesting. I don't know if that's, again, this is sort of an unofficial slide. It may not actually mean anything, but it is interesting that there is that distinction made between Kaveri and its Bristol Ridge replacement.
Yeah, I think that, I think they integrate the South Ridge, and I think that the reason that Summit Ridge is not tagged as an SoC is simply because it doesn't have integrated graphics. Presumably that's because you'd use a discrete graphics card with that, or that same chip is probably going to be used in Opteron space, like in servers. I assume it's called the Opteron, but something in the server space, presumably. So, we're going to hear more about this soon, and probably have some good information. So we probably shouldn't press too hard on this little bit of maybe not correct information. But
yeah, I could have whipped this up in Photoshop in about an hour. So,
if you did that every so often, people would just flow to the site. The traffic would be amazing.
Wait, are there other sites that do that already?
Here we are talking about this, and who knows who made this thing up, right? So,
yeah.
I don't know. All right, but let's move on, because we don't freaking know anything really. So, but hopefully, I think May 6th next week is the Analyst Day, and presumably, if these slides are at all correct, they're going to be sharing. AMD is going to be sharing information about its new stuff at that time, and hopefully, we'll have some official talk then. So, another thing that's going on this week is the Build conference that Microsoft puts on, and Mr. Campman, you tuned into some of this, and there are a few bits of news that came out. So let's talk a little bit about the Windows 10 web browser, which was, I guess, originally Project Spartan.
Oh, yeah, this for the longest time, basically about the fact that Microsoft was coming out with a new browser to replace Internet Explorer. It's been called Project Spartan. And I guess Microsoft's PR department told Fiore that he couldn't use that name anymore. So they gave it they revealed the official name this week, and it's called Ed. For what it's worth.
And so
the Internet Explorer replacement. It's Microsoft.
I've been following
Edge.
this story of a new browser for Windows for a while, and I have to say, I'm having a hard time with this. People are excited about the fact that Microsoft is making a new web browser that's not called Internet Explorer, right?
Yeah.
Do you remember when Windows 8 was being developed, how Microsoft was rebuilding the web browser for that from the ground up?
My memory's a little hazy.
Like, didn't this happen?
Yeah, I mean, I guess kind of like ever since the way I remember, like ever since IE6 was there was back when IE6 was dominant, and then Firefox and Chrome were the up and comer. There was like this gradual shift from Microsoft where gradually became more standards friendly, gradually became gradually became a better performing browser through IE 7, 8, 9, 10. I guess we're up to 11 now. Now is the last one. But, by that point, nobody really cared, I guess. Like, Chrome and Firefox had already taken over the market. So, it's like, all right, well, that's nice, Microsoft. You're doing a thing with your browser. But it never like this kind of buzz around it, I guess.
Well, I mean, changing the name is one thing, and clearly there are new guts. Yeah. Like, they've built like a new, supposedly faster, nicer core, more modern core. But I swear they rebuilt the core during the Windows 8 development process, or like right around that time. And remember, because they needed to be able to browse well on lightweight devices like little tablets and convertibles based on Atom processors, and Windows RT too, like they were going to use ARM. And they came up with a whole new browser, and everybody was like, oh, this is much better and much more modern and all this, and now we're doing this again. I don't know.
Right.
I just, Jeff follow me, like back me up. Don't you remember?
I don't know
this?
why people get excited about it. There are all sorts of I mean, people have been excited about it because I think everybody likes to hate on Internet Explorer, and this is seen as, I mean, they also very much pitched it from the very beginning as a departure from Internet Explorer and a separate thing, as opposed to we need to fix Internet Explorer for tablets. It was, we're coming up with an entirely new browser. So I think that's why, tech sites sort of picked it up and started paying more attention to it. But I mean, it's really hard for me to get excited about another Microsoft browser. I mean, I don't even mind Internet Explorer 11 in sort of on a tablet in tablet mode, because there's no way to use Chrome on a Windows 8 tablet like that. So I don't actually mind it, but I just don't really get excited about web browsers either. So
yeah, obviously rebranding is important because their Internet Explorer brand is terrible, and clearly like they could do better. So building something new is nice, but they did just build something new for Windows 8, and it was a pretty big departure and described as more lightweight and modern and all this stuff. So anyway,
this one's different though. It's a platform. It's not just a browser.
Yeah,
because it has extensions.
It's got extensions. Yeah,
everything's a platform now and a service at the same time.
Right.
And we might get into it a little bit, but like one of the things they really emphasize, I mean, because Build is a developer cost, right? So they're really emphasizing like how easy it is to build for Windows, or for Windows. So like with Edge, with the extensions they emphasized in the presentation, like just you could port over your Chrome extensions with just a few modifications to your code. I don't know if Firefox extensions work the same way, but they seem to be trying to put on a welcoming face, like especially for developers, which historically has been a huge problem for them. And again, we might talk about that in a second, but
yeah, well, let's talk about the other story you wrote, Jeff, because I'm not sure that working with developers has been a problem for Microsoft. That's always been a strength in my view, but
sure.
they do have a problem with apps, and they have a problem with other things where they're losing, right, in some of these new ecosystems.
Well, I guess I should emphasize, like, they have a problem on mobile, like Windows Mobile. The traction of that platform has not been good, and I think that that's my meaning more than like the desktop. Like obviously we don't have any problem with Windows, but like mobile space is, I think, something they're still trying to crack into maybe. So, but yeah, so this other article I wrote, like the big theme they were thinking about was just like getting Windows on more platform devices, and so they said, like, we want to get Windows on 1 billion devices, because with an installed base that large, it's very difficult, I guess, to ignore like the Windows 10 platform. And so they wanted to do that 2 to 3 years, and I guess part of the way they're going to do that, I think, if you're running, I think back to Windows 7, Windows 8 point maybe, Windows 10 will be a free upgrade to those users. But they were also, we also talked about like making Windows 10 a free upgrade even if you don't have a legitimate license. They're going to work with mobile providers in China maybe to get Windows on more mobile devices. So that's, 1 billion users is a really ambitious goal. But they're like, the other half of that is like Windows 10, they were really emphasizing like developing universal apps for this platform that can shift across mobile devices, tablets, and desktops all at once. And that was kind of like the way it was supposed to go with Windows 8.1, which is like a little bit of deja vu for me. But so we'll see if it works better this time. But so
yeah, I think in the past though you had to have separate executables for like your Windows Phone app versus your Windows 8 app, and now they're trying to unify that, as I understand it. So it all scales up and down depending on screen size, but it's actually the same program. Right?
Yes. So yeah, developers. So they talked. I think once they demonstrated was USA Today. So they took the USA Today like Windows app, like you would get through the App Store, Microsoft Store, whatever it is, and they had that scaled up to a desktop size. They scaled it down to a mobile screen. they talked about a version for the Xbox One, because you can apparently target that platform now as a Windows platform, where they had just like cut out text and done just video content for it. So, this one app, multiple, like, I guess, platforms, at least platforms thing is a big thing for this.
Right. Yeah, okay, let's just pause here real quick and see.
Sure.
Mr. Campman, are you downloading GTA 5 on Steam as we speak? Because
No.
your connection to us is spotty. Like, am I wrong here, Jeff? Like, this is.
Yeah, I see it as well.
Yeah, it's hard to hear. It's hard to understand you because you're cutting out. So, I don't know if there's anything that you personally can do while we're here, or if you need to step away and go like turn the internet knob. But it might be good to.
Okay. Yeah. If it's getting, I'll flip it or flip my router back off and on.
It wouldn't hurt.
We'll see if it helps.
It wouldn't hurt.
Okay.
So I think the other thing that was a part of this story is just the idea that Microsoft's going to encourage the porting of apps from iOS and Android.
Yes.
And part of that is maybe kind of sort of like they'll have a Android subsystem that deals with all the Google services that you get in Android, so that an Android app could run on Windows and get the things that it needs to be compatible with no modification or minimal modification. Not really clear on the level of change required here. This isn't like you download things from the Play Store with your Windows tablet, is it?
No. Can you hear me any better?
I don't know. You're going to talk more.
Still. Okay. Well, okay. So, like, again, like, I don't think it's like something where you can just develop, or you can't just download an app as a consumer from the store that's originally built for Android and run on a Windows device. Like, this is something developers have to do, but they are basically including like a Java virtual machine of, I guess, runtime on mobile devices that can run Android code and provide like Microsoft replacements for Google services for those apps. Like Load Services was the big one. It's so it's easier. It's just a way to make it easy for developers to port their apps over with Fuse.
All right, dude, I can't hear you, so you go
Okay,
turn the
sorry.
internet knob or whatever you need to do, and we're going to move on to the next topic.
Yeah, sure. I'll rejoin you in like 5 minutes.
Cool.
All
All right. And all of a sudden, that means the other Jeff's camera is going to get completely hosed. So we will try to bring you back through the magic of like little things that you do in XSplit. But we're going to have to do this live. It's a live reckoning here, man.
That you can only watch, or I can only watch on a 30-second delay.
It's going to happen. Whoa. Oh, now your face is enormous. We have to start over. See, Jordan's missing out on all the fun by not being here
We don't
tonight.
even have a monkey stand-in.
No, we just totally, we're failing on so many fronts. We're failing without him, including No Chimp. The No Chimp thing is a tragedy. All right. There we go. And so our next subject is, let's talk about this. Valve removes payment options for Skyrim mods. Jeff, you wrote this up. This was maybe like the biggest little tempest in a teacup thing on the internet in the past, like in 2015, maybe. What happened?
Yeah. Well, it actually started on the 23rd. So Valve came out and said that they were opening up the Steam Workshop and allowing modders to actually charge for their work. So if you wanted to make, a mod for a game and wanted to charge people for it, you could actually set a price on your mod, or you could distribute it for free. And they sort of launched a pilot program with Bethesda and Skyrim, which has a very large mod community, a very active mod community. And I think the issue that people most took, or the point that most people took issue was the fact that as part of this deal, the developer of the mod who was charging for it would only get a 25% cut of the proceeds, and the rest would go, and it ended up being actually split between Bethesda and Valve. So they were basically, Valve was giving modders a platform on which to sell their content, but then also taking a cut itself and sort of leaving it up to the game publisher to decide how much the mod maker would actually receive from whatever they were charging. And the internet did not like this. That's probably the best. I think Gabe Newell said something about pissing off the internet not being a good idea. You could lose millions of dollars in like minutes. But you know, it seems to be mostly the Skyrim modders that had a big problem with it, and you know, worried about it fracturing the community and modders going over to Steam, and that would possibly kill sort of other modding distribution venues. And you know, potential problems with people taking free mods and then sort of presenting them as their own and trying to sell them and making profit from them, and then sort of the additional outrage of, you know, how dare modders only get 25% of the proceeds. So it ended up being something that, you know, there was enough, you know, enough voices of dissent on Reddit. There was actually a campaign to downvote or put negative reviews into Steam of Skyrim related to this. So the internet sort of mobilized and did basically everything it could, and Valve ended up retracting the program for Skyrim, at least. The page that describes sort of this concept of being able to charge for mods still exists, and the announcement that they posted was very specific about that they were halting paid mods on the Steam or the Skyrim workshop. So it does look like this is something they may revisit in the future, maybe with one of their old games or one of their own games. But in the statement that Valve released, they said it's clear we didn't understand exactly what we were doing. So I think they've sort of been a little bit humble and realized that they stepped into a community that maybe they didn't know as well as they should, and tried to do something different, that maybe they went a little bit too far, didn't properly consider things. So it sounds like maybe they'll revisit this in the future with another one of their games, but that at least for Skyrim, it's dead in the water now.
Yeah, I mean, just the idea that you step in and, I don't know. I mean, there's some parts of this that like really kind of bugged me that people were mad about. The idea that the people are upset because mods have been free in the past and they don't want like modders to be able to make any money at all.
Yeah,
that part of it,
that.
like, and you know, there's that sense of entitlement. We've seen it in other things on the internet, and like that is an ugly part of this that deserves to lose. But then you immediately get into stuff like who gets paid how much when one modder did this and the other modder took it and did that to it, and what is the cut of the original game maker, and what if Bethesda turns out to be greedy, and in this case they were, and all of that, you know. And so yeah, you probably need to start somewhere else with this. And you know, the only good thing I could say is I hope maybe Valve takes it back to the drawing board and creates something that's like a usable economy around this kind of thing. It would be neat to see a game that gets collaboratively developed and extended by people who can make real money off of doing good work in a way that's sort of productive and well-defined, and everybody understands the rights. But once you do that, you've got like Linux plus there's money involved. Like, you know what I'm saying? Like, you got free, like, open source plus there's money involved. Like, that's really hard. So I don't know whether they'll ever get it sorted.
Well, the interesting thing is they're kind of doing something similar with Unreal Engine 4 already. It's not tied to a specific game, but they've created this entire marketplace where people can sell in-game assets for the engine just in general. So it does seem to be that the gaming industry is moving in a direction towards allowing individual content creators to sell their content on sort of a wider marketplace, either directly to gamers or to other developers. So it does seem like this is something that will get sorted out at some point.
Yeah, well, and the Unreal Engine has a store, and they're doing this Unreal Tournament thing, which is collaborative, right? Oh,
yep.
We're getting Mr. Campman back. He's back.
Oh, and all the views are going to be screwed up now.
Oh, look at that. No, see, now we're good. How you doing? Are you like? Did you like go install Google Fiber?
Yes.
Hey, he said yes, and it was like the whole word instead of like yes. So maybe this is gonna work now. That's good.
We can hope.
We just finished talking about Skyrim mods, and it was sad, and now they have to do better. You know what we're going to do now is mess up the cameras even more because it's time to bring Riss on, who wrote this excellent article for us on
Yes.
semiconductors from idea to product, which we published this past week and which we are now going to talk about. But we have to bring him on, which means we have to add another person to the Skype call. And then we have to totally hose up our cameras. So it's probably good that Jordan isn't here. Let's see if we can bring Riss in, and then we'll just see what we can do about the cameras, guys.
And then we have to totally hose up our cameras.
I hear something.
Let's see if we can bring Riss in, and then we'll just see what.
Oh.
Hello?
Hey, there he is. Where is he? Can you join us with your camera on?
I think the camera is
I
on.
see him.
Yeah, I see him.
Weird. Why don't I see him?
Is Skype bugging you to accept the video from him?
It is not. It just isn't showing me video from everybody. It says 2 participants. Riss, I'm glad you joined us, but I wish you had joined us completely in video.
Yeah, we maybe should have tested this with more than just me and you.
Well, you know, we've done this many times and we've never had this particular problem, so it's always something new. Which is great, right? Oh, now we've got, oh, I had dynamic view turned on. I have no idea, guys, how we would go, how we would add the camera. How come
I
you
don't
guys
know.
see him?
I
What, do
already
you
see
see
it.
me? Do you
I
see?
don't know.
Do you see him and me?
I see.
Yeah.
I see.
Your window never shows up correctly. You either got some sort of weird XSplit window,
Oh,
or
I do have a weird XSplit window.
but no, I see 4 discrete cameras.
And it's fine, I'm not that good looking anyway, so you're not really missing me.
I'm completely baffled by this computer technology. How could this be so hard? I completely don't get it. This is why we should be using Google Hangouts, guys.
It's maybe because I'm using a Mac, right?
Yeah, I'm sure that's it.
Let's blame it on Apple.
Briss, why don't you drop out and I'm going to try and add you one more time.
Okay.
Because I got nothing. Like, that's all I got. So hang up so I don't have to hang up on you because I can't hang up on you because Skype is totally hosed.
He's gone on my end.
Is he back?
Yes.
And apparently, we're not gonna get video of you, Riss. You guys have video of him? You can see him?
I
That's
can
not
see him.
fair to me.
Oh, you saw him last week, though.
I did.
You saw me for days.
So last week I went and visited ARM, and they had a little event in London. They talked about the Cortex A72 CPU, which we're going to talk about if we get the time later. And during that time, I stopped by and saw Riss, who lives near London and who was part of the TR London meetup, which we did on, was it last Friday night? and we had like 7 or 8 guys come out and drank beer with us at the pub, and it was a good crowd.
Yeah, it was really good fun.
So it's pretty cool to be able to just be somewhere and be like, hey, maybe we should do a meetup while I'm here, and just get on the internet and be like, if you want to join us, then go ahead. And we had a great crowd of guys, and one of them actually was a guy who goes to the Lee Summit, Missouri, where I live, the Kansas City area meetups, and who happened to be in London that week, and so he showed up there. So he wins something for that. But then it was just good conversation. You know, Riss, I think the hardest thing about that was just that it was like it was like being on the podcast for like 2.5, 3 hours, because it was just constant conversation about different tech topics as we went.
Yeah, we didn't talk about anything but technology really. So yeah, it was good. I really enjoyed it.
No, it's properly nerdy and fun. So yeah, and it was a good time. So Riss, we want to talk about the article we published last week that you wrote for us about semiconductors, from idea to product. And so your day job is at Imagination Technologies. So tell us a little bit about who they are and what they do.
So yeah, IMG we're a semiconductor IP supplier, so we don't make silicon chips ourselves. Well, we kind of do. We make test chips and stuff, but we sell the kind of the building blocks of modern kind of consumer chips, the things that you kind of find in your phone or your tablet or your car or a whole bunch of other stuff. But I guess the stuff we're mostly known for is our graphics IP and our video IP. So little GPUs and video cores that consume not too much power these days. They have to not set you on fire when you're using them in your pocket and stuff. So, but yeah, small embedded bits of semiconductor technology that we sell to chip vendors, and they take it from there. We give them the source code basically, and they produce chips based on that, on our design. So, and my day job is to convince new customers that it's a good idea to buy our stuff. So I do the technical pre-sales, and then when they've built something, I also help them figure out how fast it is versus what else is on the market, and help them speed it up or compete very well against the stuff our competitors are selling. So I come kind of involved at the start of the process and right at the end as well.
So what you've done for us is you've written kind of an overview of how a chip gets made, starting with kind of like the idea, the concept of what a company that's making a chip would want it to be, how they would define that, and then taking us through all of the stages of this. So I hope that some of the folks who are in the chat and who are listening have actually read the article or are familiar with some of this stuff. I don't know if we want to walk through all of it, but let's start up front by saying that what I'd like to do is open up to the chat questions. Risk, you're willing to answer whatever as long as you can about sort of the process and how it works.
Yeah, I can talk about the whole thing top to bottom. If I can't answer something, then I'll say so, but it's highly likely that I can probably answer almost all questions.
Okay. So guys, if you're in the chat and you have questions about how things work, how chips are made, the process is described somewhat in the article, quite nicely actually, but if there are details or things that you're wondering about, curious about, then put them into the chat, and we'll try to get Riss to answer them for us. So this is sort of a from inside of the industry look at how it all goes. Maybe, Riss, can you give us a quick overview, a step through the process involved? I think one thing is just, well, let's start with the question of the idea of a chip. How does a company decide this is what we're going to build and this is how we think it ought to look so far ahead of when something comes to market?
Yeah, there's a reasonable amount of just crystal ball gazing, like kind of trying to not guess, but you're kind of looking at the history that's already happened. You're looking at where you think the markets are going to go. You're looking at kind of, I don't know, geographies, countries that may not be wealthy now that might be wealthy in the future, that may be able to afford some new technology. And you're kind of thinking about a whole bunch of stuff, process technology, whether you're going to have the kind of the the technology available at the silicon level to make something new that you might want to sell in the future, and what kind of performance leap you need from the last time. And so you're trying to predict the future a little bit. You're trying to gaze into this crystal ball about what chip you want to make and what performance it should have and how much it should cost and what it's going to cost you to make it. But unless you're trying to invent a new market, it's a chip to go into something brand new. You're kind of building. You're standing on the shoulder of giants, right? You know what came before, and you kind of should have a good idea about what should come next. So the ideas are not always brand new, but you're trying to predict the future, but using a lot of knowledge that you just kind of already have because you made something before, somebody else made something before, and you want to try and have a go at that yourself.
Right. So the chip that goes into the next iPhone is probably a progression from the chip that went into the last iPhone, et cetera, et cetera. What about how long does it take, just process from start to finish, to make a chip?
So it depends on whether you're going to do any of it yourself. And by that I mean design the kind of the blocks on the chip, the things that are actually going to do stuff, CPUs, GPUs. If you're just going to buy IP that's available in the market from maybe guys like us, IMG, or ARM, or whoever else is selling IP, then and just do the integration and then the physical manufacture and sell it, you can actually do some companies can do something in like 3 to 6 months, right, from start to finish. That soon.
That's insane, right? That's new. That's a new thing that's happened in the past few years, right?
Yeah, I mean, guys like MediaTek, Spreadtrum, Rockchip, those guys can take a bunch of IP off the shelf, do the physical integration, create the kind of the physical representation, the GDS2. I talk about that in the article, the masks, and then get something out to market, including testing and device integration in well under a year at this point.
And so that's one reason that works, is because they're taking something from, like, say they use graphics from you guys or a core from ARM. They're taking something that's already been it's already been tested and validated, right? Like, not necessarily in silicon, but in pre-silicon stages.
Yeah. So say somebody buys a GPU from us. We've already gone through the design process, the architecture. We've tested it. We've run the driver on it on the emulator. We've maybe done a test chip. So, but that process for us is like a 2+ year process. If it's a new architecture, we can do new revisions of the architecture in about a year. But there's still that kind of year ahead of anybody buying it, where we've been working hard to make the thing. Usually 2. So it's that kind of timeline ahead of time to develop the IP, and then somebody can take it. So. The stuff I'm working on right now, the GPU architecture, I'm helping to kind of figure out at IMG. That's not going to show up in silicon that you can buy in a phone or anything for about, I don't know, 2 to 3 years. So those timescales are there to bound the whole thing. But if you're just taking IP and making a chip, you can do that in under a year.
Right. So even the guys that are doing it quickly are basically taking something that started a long time ago at a different company, pulling it in, and then putting it through their process without having to do that same work a second time.
Yeah, that's right. The big IPs on modern SoCs, so CPUs and GPUs, it's all, at least for the major architectures, at least a couple of years to come up with these things beforehand.
Yeah, and so the number that I've heard for like big chips, like say you're an Intel and you're doing almost everything themselves. Yep. And you're starting from scratch on something new. A number I've heard is something like 4 years. Is that still about right, or has it gotten compressed, you think, down to 3 years for a clean sheet design or less?
I mean, maybe if it's a completely brand new microarchitecture and they've never done anything like it before, like a clean slate design, which it's very rare in the CPU industry, at least, for that to happen. Mm-hmm. Those can take longer, so kind of 4 to 5 years to kind of shake out and get all the way to the end. But it's hard to, you kind of don't want to shrink the cycle almost to be like a year or kind of like that for CPU architecture, because the way the market wants to accept new products, the cadence it wants to kind of take new silicon on, and just how expensive it is to manufacture now, and how hard it is to use kind of tiny geometries and kind of cutting edge silicon processes. You don't really want to do something new every year anyway, right? It's fast in the SoC space for phones and stuff, but it's legitimately longer in the desktop and kind of laptop space because of other market forces. So.
Okay, so there are several things that you can do before you even build a chip to sort of vet a design or an architecture or something to figure out it's going to work and hopefully perform well and all of that. And we got a number of questions in the chat that are looking really good. But we probably need to get this distinction in before we go to that. So tell me, let's talk a little bit about what is simulation when you're building a chip, and how is that distinct from emulation and FPGAs?
Okay, so the core distinction is that a simulator is just bit accurate, so it produces the same results as the real stuff will, but it doesn't do it exactly in the same way, clock for clock. So you put the same inputs in, you run your computation, you get the same outputs out as the real chip will do in the future, but it's not cycle accurate, so you can't really tell how fast it's going to be at that point. You can just tell it's going to work. So that's the simulation side.
And that runs on like a big bank of computers before you, like relatively early in the process. Is that the deal?
Yeah, it's kind of the first step. It happens before emulation usually, and you can run like our simulator for our GPUs. It can run on a desktop PC. I mean, so I run the simulator fairly regularly on my machine at work, and it spits out frames of rendering. It takes a long time to do so, but I'm not really using it to check performance as such. I'm just using it to check that the GPU is going to work for a certain thing that I've done. So what
does the simulation rate look like? Like 1 hertz per something? I mean, do we have a number for that?
Oh, the rate it's going to be way less than like a megahertz. Like it's a tiny amount of kilohertz, probably even less.
Wow! So
we're talking about like I've got a high-end CPU in my machine, and just a single core of that CPU is able to churn out a frame, depending on the resolution and the complexity of the shaders and stuff, in like 2 to 3 hours. Right? It's that kind of time.
Wow! So yeah, that's rough. So
pretty slow.
Yeah. So what then is emulation, and how is it distinct from simulation?
Okay, so emulation is where we're taking the actual final RTL, the source code for the whole design, and then pretending that it exists in silicon and running it as if it was silicon. So it's cycle accurate and functionally accurate. It's as if the chip was actually executing. And so the emulator systems that can do that, they're incredibly large, incredibly expensive. So millions of dollars. They're usually rented. Actually, it's rare for chip vendors to actually buy them. They just rent them from the EDA tools vendor, and then that thing runs the whole IP, so the whole GPU, at a rate of a very small number of megahertz to potentially a high number of kilohertz. So it's kind of 1 to 2 megahertz for the GPU. So we're not going very fast, but at least it's the full GPU. Or the full IP, no matter what it is. It's running at that kind of a rate, but it's the actual. It acts like the silicon would.
So every little gate and bit, everything that's in the chip, eventually you can run it in an emulator and see how it goes.
Yep, all the flip flops are flip flopping at that point. Yeah.
And okay, tell us about FPGAs. What are those, and what do they do for this process?
Yeah, so you can think of the FPGA as kind of like an emulator. It takes as input not the RTL as such, but like a compiled version of the RTL. So it's like a gate level representation, not the source code level. So it's kind of one level down, and then you bake that into the FPGA using a set of tools. And the FPGA is basically just a huge array of configurable gates that you map your design onto, and then it acts as if it was the real chip again. A little bit faster than the emulator, but you can't fit large designs into most FPGAs without splitting it over multiple FPGAs. So the biggest FPGAs on the market today, we can only fit our smallest GPU designs onto, and even then it's like a bit of a squeeze. So we can't put like a large 8 or bigger clustered GPU on a modern FPGA, a single FPGA at least. So that's the kind of just size that you can fit the IP into, and it runs a little bit faster than an emulator but it's a fraction of the cost. But you're kind of constrained by the size of your design.
Okay, so now that we have that distinction established and kind of have a little bit of a start, there's a lot more to the process from end to end to build a chip. But I think we can probably seg into some questions from folks in the chat. And also, Jeff, if you guys have questions for Riss, like, you jump in here, or maybe help me pick out some questions from the chat. I'm going to see if I can find the first one, and maybe you can help me after that.
Sure.
Let's see. So, let's say Checula wants to know, in practice, how good are the simulations between what you expect and what you have, or what you expect when you have an RTL, and what actually happens in the physical test chips. So there's a lot that happens when you make a physical version of a chip that probably an emulator won't really tell you. But how good are the emulators at predicting things?
So we use the simulator to verify that the chip in emulation is actually correct. So we use one to verify the other in a lot of cases. So say we're running a chip under emulation and it produces like a few pixels worth of error in the image. So we're working on a GPU, and then we'll go back to the simulator and verify that the simulator is doing the right thing, or we can reproduce the error, and then we change the simulator version to fix the thing, and then we bake out some new RTL, and then we put that through the emulator and we check that it works. So we're using the earlier stage in the process, the simulation process, to actually verify the chip is correct in emulation if we encounter problems.
Okay. Yeah, I think I messed that up with simulation versus emulation when I passed it along. But Jeff, are there other questions in the chat or questions you guys have?
Another interesting one was, I think, Power666 asks how much of the design is typically tied to a particular manufacturing process when using, he says, quote unquote, portable design tools. And I guess by that he means stuff like RTL.
Yeah, so the RTL we produce, we tend to have, so we know who our customers are probably going to be, and we know who our customers are going to use as a foundry most of the time, at least. So we have some process technology in mind when we create a new kind of revision of the architecture or a new series or something like that. So like right now, Series 7 of our GPU IP, we're kind of targeting kind of 16 or 14 nanometer FinFET kind of process, not the kind of older stuff, 28 or what have you. So we always have something in mind, but the RTL is kind of foundry agnostic. So a customer can take it and put it through whatever foundry they like, Intel, Samsung, TSMC, UMC, Global. We don't really care, and we can help the customer do a good job on whatever process technology they want to choose and whichever foundry customer they want to use. And there are tools and libraries and things that we can help them do a good job in their chip in silicon. But as far as we're concerned, we have to be kind of foundry agnostic at the kind of RTL level. We don't know what our customer might use, so we have something in mind, like I said, but we can go anywhere. We can go to any foundry and still have a working chip.
A question from Layer Up. What methods do the hardware teams use to optimize the block placement on the silicon?
So it's kind of funny. The first time we do a new architecture where we've never put it in silicon before, nobody's ever done anything with it, we just we don't guess at how we should lay it out that's going to be good for the customer and how it's going to time well and everything. But we have a good stab at it because we know roughly how the blocks all fit together, of course, right? But after the first revision of an architecture, when customers have actually taped these things out and made chips, then we take feedback from them about how hard it was to lay out, or how easy or how difficult it was to close timing across the whole IP. And because when you clock a block, the clock kind of propagates across the block in like a wave. And if the wires that connect each part of the block if they're too long, or the clock gets skewed, or there's a delay when the clock is traveling across the IP, then you have an unstable clock and the design won't work. So and layout can affect those kind of things. So but we we try and aim for our designs to come out kind of rectilinear, square if possible, easy to lay out, easy to place into a larger design and integrate. So we're doing as much as we can to help the customer, make it easy for them to take the IP and do something with inside of a full chip. So that's our goal, to make it simple for the customer to do that, and we're trying to make the layout as easy as possible in that way. If I could show you the floor plan of a whole bunch of other chips, you'd see kind of crazy layouts. GPUs that are kind of physically disconnected from each other. Blocks are not connected. There's a whole lot of routing channels, and they're not kind of nice square or rectangular IPs on the floor plan. So we try and do a good job there. Most of our stuff is kind of square and easy to look at and easy to find, but other designs are not quite like that. So, but yes, layout does have a big effect on how the design actually performs physically. So
speaking of that, take us through a little bit what happens with clock, and why is that a challenge? Why does that affect things?
It's mostly a function of how complex the design is. So like I said, the clock has to propagate across not just the IP but the whole chip. Especially if there's only one clock domain, for example, all of the chip has to function in a single cycle, right? The clock has to go across the whole chip, powering all of the IPs that are on there, and work and be stable. So, but as the design gets more complex, it's harder to basically have the wires between the blocks to have the clock flows across those wires, it propagates across them. So it's kind of a physical complexity problem, a wiring problem. You need to connect the IPs to each other with tiny little wires, right? It's not magic. There's no the bits don't teleport from one block to another. There are tiny little wires that connect all of these things, and so it's block complexity, layout complexity, and connecting them up with the tiny wires, and how many layers of metal you have for these wires. That's the biggest problem in getting a stable clock. Just connecting everything up.
Guys, you have other questions for him?
Oh, I'm taking it all in. It's very edifying.
Yeah, it's cool, right? It's
amazing.
Interesting
Yeah.
process.
So I got one. Is the metal layer stuff, is that done by the same teams that are doing the layout, or is that kind of like a fine art that people would specialize in something that specific?
Yeah, so when we're designing the IP, we have to think about how it's going to be connected up. So we have an idea of how many layers the customer is going to want to use to connect the block to, well, the bits of the design to each other. So one part of the GPU design to another part, but also into the outside world and the rest of the chips. We're always thinking about that, how many wires they're going to need to talk to the outside world as it is. But the wire placement and the routing and everything, that happens usually in a computer. So the design tools, the EDA guys supply, a computer just figures out the optimal layout for the wires in the metal stack. So humans can help, and sometimes humans have to help because the software can't even figure out a solution to actually connect everything up with the number of layers that you have for your design. Obviously, more metal layers are more expensive, so you might want to constrain the cost of your chip by just having a shorter metal stack. And sometimes the computer can't help you figure out how to connect everything up, so the human has to get involved. But it's mostly an automated process. You just ask a very large grid of machines, sometimes thousands of cores in a big cluster, right? A huge racks and racks of machines to just come up with this solution to connect everything up. And it's usually just a software-driven process, but humans can get involved with some parts of that. But yeah, normally a machine figures it out.
So let's talk a little bit about the way that the RTL, the program language of the sort of software image of a chip, gets turned into something that goes into hardware. You've got a section in here about synthesis, and that's kind of related to what we were just talking about, but take us through what exactly is synthesis? How does that stage fit into things?
So synthesis is just kind of it's like you said, it's the transformation from the RTL, which is source code. It's like just like any other kind of programming source code. You can see numbers being added together, right? You can see data flowing from one register to another in the source code. It's human readable. Humans write it, right? And the synthesis part is taking that, which is kind of an abstract representation of the logic and how it all fits together. The synthesis is turning it into something that the lithography tools at the foundry can turn into actual transistors. So this is the synthesis. The output of the synthesis process is something called GDS2. It's just a file format, but it describes physical things. It describes transistors, and so it's kind of just it's a multi-stage process in the software, but you can think of it as a single step where you're just taking source code and you're translating it to something physical by means of just knowing how the transistors need to connect to each other to make a circuit, right? And you know how the circuits are encoded in the RTL. You know, like say a register needs to send its value somewhere, or something happens, some computation happens, some transistors need to do stuff to make that happen. So it's just a mapping, almost one-to-one of RTL describes how to do stuff. GDS2 is actual transistors that do the stuff. And it's just software again. It's just like compiling a computer program. It's a little bit more complex, takes a lot longer, but it's functionally the same process. You can think of it the same way. So the synthesis is just taking the abstract human thing and turning it into a physical transistor thing.
So synthesis is, I think, probably especially in your domain of SOCs, very common. There is a chance, though, that there's some human involvement in this process too, right? Where you have custom logic where people get in and like design things that presumably could be more efficient. Yeah.
So usually designs, almost all of the designs shipping in the world today are just built up from libraries of cells. So if you think of the GDS2 as having just transistors or cells, most people take off-the-shelf cell libraries that say you want a multiplier or what have you, and you've kind of encoded that in the RTL in a certain way, and then you're going to use a certain set of cells to embody that RTL in the synthesis in the GDS2. And you can buy those kind of off-the-shelf cell libraries from the tools vendor, so Synopsys or Cadence or what have you. Or if you're really clever and you need to do something very specific and have the hardware perform in a very specific way that an off-the-shelf cell library won't help you with, you can design these libraries yourself and tweak how they are actually laid out and how they're placed on the silicon, and really do a custom job that is specific to you and your design and isn't going to be kind of embodied in anybody else's design that used the same cell libraries that you did. So yes, humans can get involved here. It's quite rare. You have to be doing it for a very specific purpose. It's very expensive. And often if a foundry, if you deviate from using the cell libraries they understand, they won't help you if the chip is broken at this point, if you've done it all yourself. So it adds cost, it adds risk and everything, but yes, humans can do this, and it is possible, but there's a lot of risk and cost involved.
And my sense is that the place where you might see this type of custom involvement in the past has been the big x86 CPU cores, like right in the middle of those. But there is kind of a continuum here, right? You can get involved and poke and prod in changing things without getting completely down to like the super granular detail level when you're trying to maybe optimize a design, right?
Yeah, it all depends on how much money you have effectively, right, and time. So the Intels and the Qualcomms and the kind of the design houses guys who are making chips where there's just a lot of cash in the bank to help the process along. It's more likely that they'll attempt something along the continuum, but if you're just trying to get something out quickly, or you don't have a lot of money to do so, or you're somehow cost or time constrained, then you're likely to not attempt that and not take the risk. It's just a trade-off of like performance, power, and area, but it's not very common in my opinion. Even I guess as a trend, even in the kind of big expensive chips, to do that. You kind of want to not tweak if you can get away with it, because it just adds cost and risk and time and everything. So
right. So let's talk about taping out a chip. This is sort of the next step of the process here. People, I think, hear about tape outs on the site because we talk about so and so. Like if we hear rumors such and such is taped out or whatever. What does it mean when a chip tapes out?
So tape out is basically taking the GDS2, the kind of the physical representation of the transistors in the chip, and turning it into a set of masks and some extra data to then kind of go into the foundry and actually be produced by the lithography onto the silicon. So it's the tape out is making a mask or a set of masks, which you then shine light through, and then it's kind of exposed on the silicon, and the actual physical process of making transistors on a piece of a silicon wafer actually happens. So the tape out is producing a mask set, and tape out in my line of work usually just means somebody has shipped the GDS2, right? It doesn't mean that they've gone and created the masks themselves. The masks tend to be made by a third party, even in large semiconductor companies' cases, right? Qualcomm or Intel, maybe Intel do their own masks, but it's not common to do that. You usually ship the GDS2, and then a third party, usually in Taiwan, will create the masks, and then they get sent to the foundry. But yeah, the tape out process is the mask set creation. And it's called tape out because it used to happen with, well, I found out this week after I wrote the article, actually. I thought it was because the physical representation used to be shipped on tapes rather than like across the internet or CDs or whatever. But it's actually the very, very first mask sets for the very, very first semiconductors ever made were actually tape on a see-through substance, right? An actual humans laying it out with tape across the thing, right? So that's the very, very first origin of the word tape out. But there's no tape anymore. That's not how it works. But it's a historical term that's kind of come along with the chip manufacturer.
Yeah, that probably wouldn't work very well for the process tech that we have now.
Yeah, you would need some really steady hands and some crazy tape. Yeah.
That's an understatement there. But
Yes.
yes.
Yeah, so, yeah, kind of a hangover term, but a cool term anyway. It has some history, and it's nice that it's kind of come along for the ride.
Yep. Let's see. Do we have other questions, guys, that we want to throw at him here from the chat?
Yeah, there's one from Power666. How does adding pipeline stages into a design affect clock propagation?
Yeah, so the rule of thumb is the longer the pipeline, the higher you can push the frequency, because you just have more chance to kind of propagate the clock for a given stage before something has to happen to move data or whatever is happening to the next stage. So it's one begets the other, right? The longer the pipe, the higher the clock usually. It's not always the case. Sometimes you want a longer pipeline not for frequency reasons. You want it for, ease of design, or you have something else in mind, area or power or something like that. But usually, number of pipeline stages correlates kind of directly to frequency that you're able to achieve. It's not always the case. We've had designs where the final clock the design is able to achieve has nothing to do with the pipeline length of the main kind of ALU hardware, right? It's maybe timing on a memory somewhere on the design. It's maybe not the pipeline length of the main compute core that is causing you your clocking problems, but or the clock that you can achieve. But it tends to have the biggest effect. It's the thing that tends to, at least for the compute stuff, the ALUs, it tends to have the largest effect on what frequency you can achieve reliably. I mean, other things play into this, right? Voltage is another thing, like with the minimum voltage you need for the transistor to switch reliably and not and kind of produce the 1 or the 0 that it's supposed to produce, right? So it's other things have an effect, but it's kind of pipeline length is one of the big ones.
Do we have other questions?
Not from the chat.
We caught up. All right. We could. There's a lot to this, so I feel like we could probably keep going for a long time, but we maybe shouldn't.
No, that's okay.
Yeah,
We could do a 6-day podcast, or you guys could kick me off and carry on with something else. So.
Yeah, we'd have a few other things to talk about on the show. So
No, that's fine. I think I've probably taken up enough of your time already. So
But
feel free to kick me off.
thanks very much for doing the article and for educating everybody and for coming on the show. And I think what maybe we need to do is one of the off weeks when we aren't doing a regular podcast, maybe have you on, and we could do even more of this or some other in-depth stuff. So that would be, I think, really helpful.
No, I'm happy to do that. Yeah, no problem.
Excellent. All right. Well, thanks, Riss.
Welcome.
Maybe next time we'll get your camera working. I will try. I honestly, I think the answer is don't use Skype, use Google Hangouts, but we'll see. But I'm gonna have
it's completely your fault. It's not my fault. Right?
It completely must be. Anyway.
Okay. Yeah. Thanks, guys. It was fun.
All right.
Thanks, Riss.
Thanks. Take
Thank
care.
you.
And now we have lost Cameron. Apparently he thought, oh, Riss is leaving, so I'll just leave too. So maybe he'll.
You'd think the internet would work better than it does.
We are weeks from Google Fiber hosting this show. We are weeks from that. And I don't think it's going to change anything if Cameron's internet doesn't work, right? Because my internet's connection is not the problem here, people. But it will be awesomer soon, hopefully. So just weeks. Jeff, I think the next thing on the agenda is
Chat questions? No, compute stick.
the compute stick. Tell you what, if you're in the chat and you didn't have a question for Riss, but you have a question for us, or you want to talk about something, put your question in now. Now is the time to get it in there so that we can get it talked about before the end of the show. So there are a couple other things that I've been working on that we should briefly chat about. One of them is the Intel Compute Stick. And so this thing pictured here is, I just reviewed it briefly last week, and I think Cam is coming back. Is he coming back? There
I am
he
here,
is.
right?
All right.
My computer just straight up crashed.
Wow.
Yeah.
That's a new one. I just, for the record, because it hasn't happened yet, we are hosting this on my new PC, which I will be writing about very shortly. The Damage Box 2015. This is the first time we've hosted the show on the thing, and so far we've only had minor disasters involving Phantom Skype windows. So we haven't had any crashes yet. I haven't done the thing that you would want to do before you get your new PC into production, which is figure out how fast the memory will run. So it's default whatever, I don't even know, clock speed. I need to spend some time in the BIOS, and I haven't done it. So, but so far, no crashes. So that's good news. But we're talking about the Intel Compute Stick. And honestly, guys, I think a review of this thing is kind of just like an overview of the concept and then sort of saying whether or not it works, because that's kind of what you want. I didn't spend a ton of time running benchmarks on this because it's kind of familiar territory. This is based on a quad-core Bay Trail chip, which is Intel Atom. It's got built-in graphics, everything all in kind of one chip. It's got 2 gigs of RAM, 32 gigs of flash-based storage, and it's on basically an HDMI stick. So it's kind of bigger than a pack of gum, but not much. Fits into your hand. You plug it into a TV, presumably TV with or monitor with sound or something like that, so that you can get a picture and sound out of it. It's got one USB port and Bluetooth, so you could use either of those means to connect to keyboard and mouse. And it has Wi-Fi, so it's got the connectivity there. And it comes with Windows 8.1 with Bing, which is the sort of free version of Windows that you get on certain devices. And it has an SD card slot that it'll hold, I think, up to 128 gigs of SD card storage. And so you can expand the storage on the thing that way. And then it has a little power button on the side. So you connect this stuff, you turn it on, and you have a Windows-based PC, like a full system, wherever you have like a keyboard, mouse combo, and a TV. So it's kind of a nifty idea. It's $150 as configured, which seems like not a bad price. There are some cheap Bay Trail tablets that maybe cost that much, and it gives you a nice little streamer. You can run Netflix on it. You could use it for maybe Steam in-home streaming, although you have to maybe have a either an Ethernet adapter or a better Wi-Fi adapter connected via USB to get like full speed for that type of streaming. But anything that you want to do with a basic computer, it's going to do it. And really, installing software and running stuff on it isn't that bad. The real limitations of this concept that make it a little weird are you have to have a power source, which is a USB input. And so you plug it into the wall, or like if your TV has a powered USB hub, then you can do that. I tried it on a monitor that didn't have a powered hub, and so I was just creating like a little loop of nothing. like it didn't work. Jeff, like, can you just plug power in briefly and then it'll just keep looping around in there? I couldn't make that happen, so I think you need an actual proper power source. And then the other thing is that because it plugs in via HDMI, but it sticks out a little, you're going to have to wind up using probably the HDMI extender that's included for most TVs and things like that. So it's going to hang down a little. Probably it's not going to plug right into an HDMI port, but really, it's pretty compact. And Jeff Gazer, doesn't this kind of feel like this is probably better than your computer that you built for yourself at some point in the past?
Oh, yeah.
Does it feel like
more cores for sure? I mean,
yeah,
it's full-on quad-core chip.
Well, and this is the Silvermont core, so it's not like the original Atom where it was kind of like the per thread performance was not good enough to really be okay. Like, this is okay, and it has like a video decoder in it, so playing video is okay. You remember the old reviews we used to do with like netbooks where it was like, you'd have like a red or a green for playing different video formats, or maybe a yellow where it was iffy. This is all they're all green here, unless maybe you go to 4K or something like that. But the peak display resolution it supports is 1080p for the graphics. So, and I think for almost any video format, it's going to be all green for 1080p.
Yeah.
So maybe H.265 maybe could be a challenge, but that's pretty rare still at this point. And H.264 is sufficient for 1080p generally in terms of streaming and bandwidth and all of that. So yeah, this does feel like certain things are over. Like this is cooked now. Like the PC for grandma. There it is, right?
She can take it with her.
Yeah. And
now this isn't passively cooled, is this? It's venting in the top.
No, I thought looking at it that it was pretty much going to be passively cooled. Anything of this size with low power, you would think, okay, but it has a fan in there because I noticed it because I'm using it and it was doing some stuff, and I loaded Internet Explorer, went to MSN's default page, and all this crud shows up on the screen with celebrities, and it's terrible. And it was running that while some installers were running in the background, and it started making noise. And so yeah, it's not perfectly quiet all the time. And my biggest concern about this thing is the only moving part in it is that fan, that blower, whatever it is. And so that's probably the biggest point of failure on the design. In terms of longevity and all of that. But it's not super loud. It's not terrible.
It doesn't spin up when you're just playing Netflix or sort of basic sort of streaming.
No, it doesn't. I watched Netflix on it some, and I haven't spent hours and hours watching Netflix on it, but I haven't noticed that when you're just doing that. It has to be doing several things, like I said, or something where it's just a process that's kind of a CPU hog in order for that to be a problem. So, this isn't going to run all your games really fast. Maybe any of your good games at all. little indie
couple
games
of Steam
or
games
simple
that'll
things.
run on an Atom basis.
Yeah, but it's not going to do that. But it is kind of just for a lot of things, you just plug it in, you plunk it down, and you're done. And it is neat, the idea of having one in your bag and being able to just take it wherever and be like, okay, now we're all going to do this. I guess you probably play Hearthstone or something like that on it.
Does it play Minecraft?
Yeah, that's a good question. I bet it might. I'm going to have to try that, but if I But if my kids know it does that, they'll never see it again. So that's a bit of a concern. But yeah, but it's a neat idea. It's a fun concept. And, like I said in the article, I don't think this is something that happens like several years ago. But Microsoft and Intel are in different places now than they were then in terms of understanding the threat from ARM-based devices based on Android and iOS. And they're willing to sell you something that is a pretty complete Windows PC for a pretty astounding price. And they're packaging them into form factors like this, and even Intel's putting its own name on it. So my hope is that they keep making these little sticks and that they improve them and keep getting better. I'd like to see like a Haswell or Skylake version of it eventually, once they can get into a reasonable power envelope for this type of thing. And that's going to cost a little more, but just a fun concept. And I can imagine like having a
You do
small
a Core M in
business
there
and-
for sure.
Yeah, I can imagine having a small business and being like, okay, I've got like 6 people here who need to do some basic job. I'm in the IT department. Here's your stick. Like, hand it in at the end of the day, and that would be it. Or a computer lab or something like that. So it's kind of fun. The only question really is, do you want this, or do you want, like, they're super cheap, it's like $200 Bay Trail based laptops out there that give you a whole computer that you could then plug into a TV, or tablets or things like that. The real competition is just other form factors, right, that maybe give you a little bit more of everything you want in a computer without needing external displays and things like that.
Mm-hmm.
But I don't know. I'm going to keep it around my house and just plug it into stuff and see where it winds up. It's already basically camped out in my bedroom as a Netflix streamer, though. So yeah, that's a compute stick, and it's kind of a fun thing from the NUC guys who've done the next unit of computing builds for Intel, and $149 available now-ish, I believe. And then there's a cheaper version with less RAM that comes with Linux, I think, pre-installed.
Yep.
And
Right.
so if you don't want to, I think it's $99 or I don't remember. Anyway, cheaper. So if you want something and you don't want Windows, that might work as long as you're willing to accept a little bit less memory and storage. So that's a compute stick, and I think it's sort of established a new form factor for PCs. If it succeeds, then I expect we'll see more. So the other thing to chat about, guys, one more thing, is what I went to London to talk about, which is ARM's Cortex H72 microarchitecture. This is the successor to the Cortex A57, which is the successor to the Cortex A15. So this is ARM's biggest core that is used in high-end smartphones, and then they're also pushing to use it in things like servers for the data center, microserver blades, things like that. So we have a first look at the microarchitecture of this, and this is actually an article that's not yet published as we put this out there. It is a preview of something that hopefully you guys are going to edit like tomorrow morning, right?
I'm sure you'll get notes from people in the chat as well.
Yeah, and whatever you see on the screen probably could be really hosed up because it hasn't been through editing. Like, I haven't even spell checked it, so I don't know, man. But let's just talk real briefly about this one, because this is, I don't think we should get into the nuts and bolts of like how many ports are in the architecture. I mean, I'll get the whole thing right there, and you can see there's more dispatch output than there is in the A57 and all that. But I think the important thing to sort of take away from this that I want to put here on the podcast is just what the A72 is. This is ARM's biggest core. It's kind of a mid-sized core as these things go, but they took the A57 and they basically went and optimized virtually everything at the block level to improve the throughput, the per clock performance, and to lower power consumption. And they actually along the way reduced the amount of area that the CPU core takes on a chip. So they did all of those things, and they've then sort of rolled that together with the goodness that you get from new process technology. And I expect next generation smartphones, at least some of them, to adopt the A72, whereas right now, sort of the A57 is one of the dominant players in the latest things from Samsung and other folks like that, including, was it the G4, LG G4? Jeff Cameron, you wrote about that this week, right?
Yes.
And so that's a Qualcomm Snapdragon chip, isn't it?
Correct. It's a Snapdragon 808. It's got two A57s and 4 of whatever the smaller cores are.
A53.
Yeah.
And so they call that big little. It's this asymmetrical multitasking or multiprocessing scheme that basically means low power tasks that are kind of lightweight run on the low power cores. When you need to do something big, then you spin up one of the A57s and you do what you need there. And I'm really happy to see that Qualcomm went truly asymmetrical and did only 2 big cores and 4 small cores. That's the proper thing for a smartphone, given the threading of the software and the way that it asks for things from the CPU. Some other companies who will not be named have built quad big core, quad small core configurations for reasons that don't make a lot of sense, including what I've heard is just the fact that in like some cultures 8 is a lucky number. And that was
It's more than 6.
and that was why like the architectural decision was made to put more cores out there. And then just as silly is the idea that just like more is better, right? So that you don't, clearly the best performing smartphones in CPU performance overall right now are iPhone 6 and 6 Plus, and they use 2 big cores and that's it. So, it's a little bit different with Android than iOS, but I think the threading situation isn't that different. A couple of big cores is probably right. So that LG G4 looks nice. The Cortex A72 will be deployed similarly to the A57 in big little configurations. You can have up to 4 A72s in a cluster, and then you probably will pair it with A53s, and it will either be probably 2 to 4 A72s and then 4 A53s.
So there isn't a new low power core to go along with this. This is just a new big core?
There may eventually be a new low power core to go along with this, but what ARM has announced now is the A72, and they have the right pieces in the A53 and the A72 to where they work perfectly well together. They have the right sort of plumbing on the chip and coherency, and then they also have the right instruction set support. So, this is basically ARM v8 64-bit instruction set, and the feature set is essentially similar on the Cortex A53. So don't think there's any reason why you would need a new small core in order to build the solution with the A72 and Big Little. It's also possible that we'll see an optimization of the A53, though, that will do the same thing. Because there's opportunity. There's definitely opportunity in the case of the A57 versus the A72. When they went in and looked at every unit, there's kind of a recounting in this article, and there's a fair amount of text on this front of how each unit from the branch predictor, fetch, decode, dispatch, down to the individual execution units for integer and floating point math became both higher throughput and lower power consumption, and also overall there's less actual area on the die of the chip occupied by an A72 versus an A57, and yet functionally they do the same thing. In fact, the A72 looks to be a pretty nice upgrade overall. And to get a sense of where it compares to the A57, you have to kind of multiply the goodness out. ARM is saying between like 16 and 50% improvement in various workloads, like clock for clock from A57 to A72. the probably you're talking about something that the average is, somewhere closer to like a 20% improvement overall. One of the big gains on this graph here is a memory is a 50% improvement. The memory subsystem was a weakness in the A57, especially because it was paired with the CCI 400 interconnect. Now there's a CCI 500 that has more bandwidth, so the memory subsystem on the chip is better, but also going on and out to the interconnect and off chip is better too. So that's where some of this goodness I think comes from. But this is a nice improvement in per clock performance. Multiply that along with basically there's a nice reduction in operating power on the A72. Mike Filippo, who's the lead architect on this thing, told us about the way that looks, and I think that the big takeaway that he had was that not only would the A72 be able to deliver more performance per clock, but it would probably be able to deliver sustained performance operating at what he called Fmax. Fmax is max frequency for the CPU. You guys might be aware that like a lot of smartphones these days, like with the A57 in particular, they'll start out at a relatively high clock, couple gigahertz maybe, as they run a workload, but over time, if it's a sustained workload, then the performance goes down as the clock has to throttle because heat builds up. A72 is substantially more power efficient as it operates, and so ARM believes that it will be able to sustain its peak clock quite a bit longer, maybe just indefinitely depending on the design, by not basically be eating up all of its thermal envelope. So that can be good. So you combine those things, basically power savings in a modern CPU can be turned into performance. That's kind of what happens, and that's sort of this scenario we're describing. So you combine more per clock for performance with more sustained clock speed, and then also the A72, they were able to basically they kind of targeted the same clock as the A57, but they're able to get a little bit more out of it. So I think we're going to see clock speeds around 2.5 gigahertz for these things, whereas the A57 was like 2.2 or so. So a few hundred megahertz extra oomph, more power efficiency, more per clock performance, and then coming soon are hopefully 16 and 14 nanometer process tech proliferating to lots of different SoCs. This is something we've been waiting for. These newer process technologies employ FinFETs, which is a new transistor structure that should reduce leakage and increase, basically allow for lower voltage operation and increased power efficiency. Again, that translates into performance, and so roll together IPC improvements, power efficiency improvements, more sustained clock, higher peak clock, and the goodness from the new process tech. And you're talking about, say, next generation phones late this year, early next year, mid next year coming out that use A72 that could have up to twice the per core performance by my sort of rough back of the envelope math than what you get right now with A57. And that's a pretty good gain. I think it's something that puts them into territory where you're beating or at least matching, maybe beating, depending on the workload, the Core in the Apple A8 that you have in the iPhones now. The question is, where will they be in terms of design wins in part, like in smartphones in particular? We know that Qualcomm is working on its own custom core. Rumor is that Samsung is working on one. Apple has its own thing. And, those are, right now, Qualcomm and Samsung are using the A57 because they got caught with their pants down on 64-bit, didn't have their own custom core ready when Apple made that move, and so they went and adopted ARM's cores. Whether or not the A72 will have the same success in those really highly visible places as the A72 is probably going to depend on how competitive it can be compared to those custom cores. It maybe is unlikely to be as widely adopted, but you can imagine, ARM has a lot of partners, a lot of people, a lot of companies license these chips, and the ones that we talked about earlier, like the MediaTek and the Tex and the Rock chips that license IP and then roll it quickly into a chip and sell it usually at relatively low cost, oftentimes into other markets like China. These things are going to be probably, the new standard for performance there. So one way or another, A72 is almost certainly going to be very widely distributed. So that's the basics of A72, and I think the other thing that really gets interesting is ARM wants to sell this thing into data centers, and the way they pitch it is that it's compared to Xeon, they basically say 2 A72 cores are equivalent to one like Broadwell or Haswell core with 2 threads. However, they can basically like fit into a smaller physical footprint and a smaller power envelope to provide that same performance. And so at the end of the article, there's this little sort of pitch that I've recounted that ARM gave for, here's what we could do in a certain amount of power compared to what Intel does in the Xeon. And it's kind of a weird case. This is sort of about very specific and maybe relatively simple integer throughput-based workloads where they can beat a Xeon, even like a Broadwell-based Xeon D on power efficiency or cost or density or all of those things. However, I think for traditional server workloads that need a little bit more complex compute, probably Intel is going to be really hard to beat. So I've kind of recounted this partially just to say, ARM believes that it has a chance to make inroads in the data center, and not just inside of the places where they play now, like network switches and storage controllers, where clearly they're probably going to continue having some success, but also moving into other types of servers. And I guess the thing to be said about that is that Cortex A72 ups the ante in terms of what ARM can do on a per core basis, on a per thread basis, compared to what they had in the past. And every time they do that and move a little closer to Intel, then they have the possibility of taking other portions of the market from Intel, at least potentially. Anyway, you can read the article if you're kind of interested in my take on that, but I think that that's something that A72 is interesting for, but it's a big challenge for them to go there. So that's the new architecture, and I think that the funny thing about this is now we know about A72. It's like Chris was talking about. It's basically RTL that's available to be licensed, and it could be 6 months, it could be 12 months before we have a product. It could be longer before we have like a device in our hands that uses this architecture. So so we're getting this information pretty early, and then we kind of have to wait for implementers to get a hold of it and turn it into something that you can touch and use and buy. So we'll have to see how that goes. So that's my spiel on that one. Do we have other questions from the chat? Did you guys see anything go by?
A lot of ARM puns.
There, yes.
Wow,
But I
ARM
haven't seen
puns.
any
Full of ARM
questions.
puns.
Too bad Jordan has missed that. I think I have a feeling that he would have enjoyed that. So yeah, I'm seeing pharmacist and harmonizing, and I think I'm just gonna scroll through that. I think that's enough.
I think we should call an armistice on ARM puns.
Yeah, I think that we're done. I'm done with that. So, all right. Well,
Okay.
I think that's enough, guys, gentlemen. I think we can wrap this thing up.
All right.
Anything else? Okay, let's talk about what are you guys working on? I'm working on this ARM thing. What are you guys working on?
I am finishing up the next edition of our general system guide.
This is the first one that you've done, right?
Correct.
And I've seen you.
Well,
going
it's
through
actually it's not the first. It's the first one of these that I've done. It's not the first system guide that I've done since we just did the peripherals guide.
Right. But I've seen you going
So-
through this process. It may be we have a little bit different thinking than Cyril had on some stuff, which is good. But it's a challenge to come up with recommendations for people based on sort of like if your budget's here, then do this,
Yeah.
and think
It's like-
through all of this stuff. There's a lot
Like,
of
oh,
stuff.
Yeah, like all day I was thinking, what do we get for just $10 more, and that thought process just extends, and then suddenly you've added $100 onto the cost of the PC. But
The answer is
I-
always to add another $100 onto the cost of the PC, because it always gets better.
yeah, but yeah, I think there, well, I'm not going to spoil it, but I think there are some good deals coming, some good systems coming for prices that are lower than our last one. So
Yeah, that Econo box is already looking awesome.
Yeah.
So, all right, other Jeff, what are you?
I've
working on?
got Asus's Transformer T300G, which is it's a little detachable Core M powered convertible. So I've been playing with that one.
Cool. And I'm also going to write about the new Damage box, of which this headset is a part. Actually, it's connected, and which hosted the podcast. And so far, we haven't crashed. So there you go. Anyway, well,
Cool.
hopefully next time. Actually, I don't know if Jordan will be back next time if we do this next week, but hopefully next time we do the full thing, Jordan will be well and be with us, and maybe we can talk about what the new Avengers movie with him. Are you guys going to go see that? See, Jeff's like, nah, I don't really watch those movies.
I'm more excited about Mad Max actually than I am about Avengers. I feel like I've seen that movie a few times already, but Mad Max at least looks like something different. So
When is that coming out?
it's in May. I don't know exactly when it is, but
The new Borderlands movie?
yeah. That's the first thing I thought when I looked at it. I was like, wow, somebody made a movie out of Rage and Borderlands.
Then you realize where the roots are. Yeah. That's pretty cool. All right. Well, thanks, guys. Have a good evening. Thanks to everybody in the chat room who joined us. And hopefully we'll do this again soon.